Hello my friends and welcome back to the You Can Do TV channel. From initial shredding to final material recovery, MTB delivers complete tire recycling solutions designed for precision, durability, and maximum yield. The process begins with the CRX2000 shear, a high-capacity cutting system engineered for rapid size and volume reduction. Its heavy-duty blades efficiently process whole tires, preparing them for subsequent stages. For TDF tire-derived fuel production, the CRX2000 shear is paired with a powerful pre-shredder. This combination produces uniform particle sizes with or without steel content, optimized for industrial energy applications. When clean rubber aggregates are required, MTB integrates advanced granulation lines capable of producing 0 to 4 mm fractions. Precision cutting and separation systems remove impurities, while granulate refining units achieve ultra-fine sizes down to 0 to 1.5 mm for specialized manufacturing needs. Material recovery continues with dedicated separation technology. The Textile Cleaning System, TCS, isolates and purifies textile fibers from rubber, delivering up to 78% clean textile and rubber yield. The Clean Wire System, CWS, targets steel recovery, achieving purity levels up to 98% based on operating parameters. Each stage is engineered for high throughput and minimal downtime. Modular design allows configurations ranging from basic volume reduction lines to advanced, fully integrated recycling plans. The result is a streamlined process where rubber, steel, and textile components are efficiently separated, cleaned, and prepared for reuse. With MTB systems, every tire becomes a source of valuable raw materials. High-performance machinery, precise control, and robust construction ensure long-term reliability while supporting environmental sustainability. From alternative fuel preparation to high-purity granulate production, MTB delivers tire recycling solutions that combine technical excellence with economic efficiency. The ATR 300 tire recycling plant is designed for efficient and environmentally responsible processing of end-of-life tires. The plant employs advanced mechanical and automated systems to transform used tires into reusable materials, minimizing waste and supporting circular economy principles. The process begins with the collection and inspection of tires, ensuring the removal of foreign objects such as metal, stones, or debris. Tires are then fed into a heavy-duty cutting machine, which separates the tires into manageable segments. Steel wires and other reinforcements are extracted using magnetic separation systems, leaving behind clean rubber fractions. The rubber is further processed through a granulation system, producing uniform particle sizes suitable for industrial applications, such as rubber mats, playground surfaces, or asphalt modification. The ATR 300 features integrated dust extraction and filtration systems to maintain a safe working environment and prevent contamination. Quality control measures are implemented at multiple stages, including particle size verification, metal content inspection, and moisture checks, ensuring the final product meets strict industrial standards. This fully automated plant is capable of handling high volumes of tires efficiently with minimal manual intervention. Operators can monitor the entire process through a centralized control system, adjusting parameters in real time to optimize performance and energy consumption. By combining mechanical precision, automation, and sustainability, the ATR 300 offers a complete solution for modern tire recycling, turning discarded tires into valuable, market-ready materials while reducing environmental impact. The primary hybrid tire shredders are powerful dual-shaft machines designed for efficient processing of whole tires from passenger to large OTR types. These shredders handle size reduction, recycling, and destruction with precision, producing rough shreds ideal for disposal or secondary processing. CM's patented replaceable insert knife system dramatically reduces knife costs by over 300%, allowing each knife to be sharpened and reused up to 6 times. With minimal exposed steel and clean chip cuts, these shredders excel in preparing tire chips for fuel markets and tire-derived aggregate. CM's advanced knife tolerances and reduced change-out times offer industry-leading operating efficiency. The Sierra REB2 2-ram baler is a high-capacity machine engineered for demanding recycling operations, capable of delivering 254 tons of shearing and baling force. Designed specifically for high-volume facilities, it is available with either a 150 HP or 250 HP power unit, allowing operators to match performance with production requirements. Its robust design enables processing of a wide range of materials, including tires, metals, OCC, PET, and paper, without the need for material changeover, thanks to its efficient free-shearing blade system. The REB2 features an oversized Bale release door and a full ejection mechanism, ensuring Bale integrity and minimizing contamination, even with rebound-prone materials such as tires. The compaction chamber, floor, and walls are reinforced with 1/2 Hardox 450 plug-welded liners, providing exceptional resistance to wear and deformation under extreme pressure. High-pressure hydraulics deliver ram face pressures of 304 psi, while hydraulic flow rates reach up to 564 gallons per minute, with the 250 HP configuration enabling high throughput rates. The REB2 can compress and tie bales securely for storage, transport, or further processing. By producing standardized bale sizes, it optimizes space, reduces handling time, and streamlines logistics. Engineered by recyclers for recyclers, the REB2 offers a combination of durability, versatility, and production efficiency. Whether producing dense tire bales or compacting mixed recyclables, it delivers consistent results with minimal downtime, making it an indispensable solution for facilities seeking maximum productivity and reliability in continuous heavy-duty operations. Hunchbend. The HSMHL 3521S baling press delivers controlled, high-force compaction for end-of-life tires, creating dense, transport-efficient bales. Designed for industrial throughput, the unit features an extra-large loading aperture that accommodates mixed tire sizes, enabling rapid feeding and continuous workflow. Siemens' stored program control coordinates all press movements with stable cycle repeatability, while integrated infrared safety curtains protect the operator during loading and compaction. A pressing force of 320 kN drives powerful vertical compression, achieving a volume reduction ratio of approximately 5:1. Manual 6-fold strapping with quick-link wires secures each bale, ensuring dimensional stability during handling and shipping. The system typically processes around 120 tires per bale, depending on geometry, providing a reliable solution for tire preparation, storage optimization, and downstream recycling applications. Millions of worn-out tires are discarded, piling up in landfills, and posing a growing environmental challenge. But what if each of those tires could be transformed? Not burned, not buried, but reborn as valuable resources. Imagine a technology that takes this stubborn waste and, through a silent, precise process, turns it into fuel oil, pure carbon black, and clean steel, all without releasing harmful emissions. This is not the future. It's happening now, inside the tire pyrolysis batch plant from KGN Industries. In the world of sustainable recycling technology, the tire pyrolysis batch plant from KGN Industries stands out as a robust, high-efficiency solution for converting end-of-life tires into valuable resources. Designed to process 10 tons of tires per day, this advanced system achieves precise recovery rates, approximately 40% pyrolysis oil, 38% carbon black powder, and 15% high-grade steel. The operation begins with the careful loading of whole tires into a fully sealed reactor chamber. Using the principle of pyrolysis, the plant applies controlled heating in the complete absence of oxygen, triggering thermal decomposition. As the temperature rises, hydrocarbons inside the rubber break down into gas vapors, which pass through a high-efficiency condensation unit, transforming into liquid pyrolysis oil. Non-volatile residues such as carbon black and embedded steel are retained for subsequent separation. Built with high-grade mild steel and finished with anti-corrosion coatings, the plant is engineered for long-term durability. The system operates on a 25 HP electric motor at 440 volts, 50 Hz, combining low energy consumption with high processing output. Integrated pollution control systems ensure compliance with strict CPCB emission norms, making the process environmentally safe and workplace-friendly. From loading to product recovery, the sequence is fully automated, minimizing manual intervention and ensuring consistent performance in every batch. The technology reflects a deep understanding of recycling challenges, combining mechanical strength with process precision. The recovered steel wires undergo magnetic separation, delivering clean scrap suitable for remelting. Meanwhile, the carbon black is refined for applications in rubber reinforcement, pigments, and industrial fillers. The pyrolysis oil serves as a versatile synthetic fuel, or as a base for further refining in industrial processes. At its core, this tire pyrolysis batch plant transforms what was once considered waste into market-ready resources: fuel oil, reusable steel, and fine carbon black, all from a compact, daily 10-ton operation. It is more than just a machine. It is a complete recycling system, designed for efficiency, safety, and environmental responsibility. Through its streamlined engineering and clean, closed-loop design, KGN Industries delivers a solution that proves tire disposal can be both profitable and sustainable, a quiet but powerful step toward a greener industrial future. Here, Maris, devulcanization technology enables high-value reuse of end-of-life tire rubber by reversing vulcanized crosslinks through a precise thermomechanical process. Unlike combustion, grinding, or thermal cracking, this method selectively cleaves crosslinks while preserving the polymer's main chains. Post-consumer and post-industrial rubber waste is loaded, accurately dosed, and processed inside the extruder under controlled shear and temperature. During devulcanization, the material softens and regains plasticity suitable for compounding. A final degassing stage removes volatiles, producing a clean, consistent devulcanized rubber ready for reintegration into new rubber goods.
At Sanlun's advanced tire manufacturing facility, the production process blends material science, mechanical precision, and automation to create durable, high-performance tires for global markets. From compact passenger cars to heavy commercial vehicles, each Sanlun tire is built through a systematic series of steps, each one crucial to the tire's safety, structure, and driving performance. The process starts with raw material handling. Essential ingredients such as natural rubber, synthetic rubber, carbon black, silica, oil, and chemical additives are received and stored under strict environmental control. These materials are weighed and mixed in large-scale Banbury internal mixers, which operate under precise temperature and pressure settings to ensure consistent compound quality. The resulting rubber mixture is discharged as dense, flexible sheets, which are then cooled, dusted with anti-tack agents, and stored for downstream processing. Rubber compounds are tailored for different tire components: tread, sidewall, inner liner, and casing. At the same time, steel wires are prepared and coated with brass to improve bonding strength, while textile cords are readied for use in body plies. In the component preparation stage, rubber is fed into extrusion machines that shape it into continuous strips for the tread and sidewall. Calendaring machines roll rubber into uniform sheets and laminate it with polyester or nylon fabric to produce carcass plies. These semi-finished parts are precisely dimensioned and collected for assembly. The tire building process is the centerpiece of Sanlun's production line, carried out on advanced automatic tire building machines. The main drum, also known as the primary assembly drum, is where all components are applied in sequence to form the green tire. The process begins with the inner liner, which is the innermost layer responsible for air retention. Next, body plies made of fabric-reinforced rubber are wrapped around the drum, followed by the application of beads, high-strength steel wires encased in rubber that anchor the tire to the rim. Sidewall strips are then laid over the plies. After these base layers are in place, the machine moves to the belt application stage. This step involves the installation of 2 or more steel belts, also known as load-bearing layers, which are reinforced with high-tensile steel cords embedded in rubber. These belts are applied at specific angles to improve directional stability, reduce tread deformation, and increase puncture resistance. They also help the tread maintain consistent road contact, ensuring safety at high speeds and under heavy loads. The tread rubber is applied last, covering the belts and forming the tire's outermost surface. Once assembly is complete, the green tire, a fully formed but uncured tire, is transferred to the curing area. Curing is done in heated presses, where the tire is placed into a mold and inflated with a rubber bladder. Under high pressure and temperatures typically exceeding 160 degrees Celsius, the rubber undergoes vulcanization, a chemical reaction that cross-links rubber molecules, giving the tire elasticity, heat resistance, and mechanical strength. The mold simultaneously imprints the tread pattern and sidewall details, including branding, size specifications, and regulatory markings. Tire production may seem simple at a glance, but it's a highly technical and layered process that combines mechanical design, chemical formulation, and digital control. Each phase, from material preparation and main drum assembly through belt application, curing, and testing, contributes to the final product's safety, durability, and performance. After curing, the tire is demolded, cooled, and sent for post-processing. Excess rubber or flash is trimmed from the edges using automated cutting tools. Every tire then proceeds to a series of quality control tests. Tires that pass inspection are laser marked with a unique identifier, allowing full traceability of production batch, materials, and process history. This code supports Silen's strict quality tracking and product management systems. Following inspection, the tires are sorted by type and size and packaged for shipment. Automated storage systems organize the tires onto pallets, which are then loaded onto trucks or into containers for distribution. Saloon exports to over 150 countries worldwide, supplying OEMs, dealers, and end users with reliable tire solutions. Research and development play a major role in Siloon's continued growth. In-house engineers and chemists work closely with production teams to refine formulations, test new tread geometries, and optimize performance characteristics. R&D data is fed back into the production line to implement design improvements rapidly. The company regularly introduces tires with enhanced wet grip, reduced rolling resistance, and extended service life to meet evolving market demands. Sustainability is also a core aspect of Siloon's strategy. The factory incorporates energy-efficient systems, waste heat recovery, and closed-loop water cooling to reduce its environmental footprint. Unused rubber is collected and either recycled or repurposed into low-impact products. Volatile organic compound (VOC) emissions are carefully managed through filtration and ventilation systems that comply with international environmental regulations. Siloon's manufacturing facilities are certified under ISO TS 16949, ISO 9001, and ISO 14001 standards, covering quality control, safety, and environmental management. This global certification framework supports consistency in production and ensures that all tires meet regulatory and performance benchmarks in various regional markets, including DOT US, ECE Europe, and CCC China. Through a commitment to innovation, automation, and rigorous standards, Siloon continues to strengthen its position as a world-class tire manufacturer, offering dependable performance to customers across every road and condition.
The exclusive visit inside Michelin's Advanced Research Center reveals a tightly coordinated ecosystem dedicated to future tire innovation. Engineers and material scientists operate in high-security laboratories where compounds are mixed, analyzed, and stress-tested under controlled conditions. Robotic rigs simulate extreme road loads, temperature cycles, and high-speed deformation to validate structural endurance. Prototype tires move through precision metrology stations, where laser scanners measure geometry down to microns. The tire is tested on an instrumented vehicle under controlled wet road conditions to evaluate real-world grip, braking efficiency, and hydroplaning resistance. Water is applied uniformly across the test track at a defined film thickness to ensure repeatable friction levels. All parameters are benchmarked against regulatory and OEM performance requirements. Dunlop Aircraft Tires operates as the only global manufacturer exclusively dedicated to the engineering, production, and retreading of aircraft tires, maintaining a singular focus on aviation-grade performance. The company designs and builds tires that withstand extreme dynamic loads during takeoff and landing, where aircraft touch down at speeds comparable to Formula One vehicles. Tire behavior directly influences braking performance, landing stability, passenger comfort, and operational cost, making manufacturing precision critical. Its UK plant integrates advanced compounding, bias and radial building systems, precision molding, and controlled curing technologies to produce tires for commuter turboprops, wide-body airliners, military fighters, heavy transport aircraft, business jets, and rotorcraft. The facility uses semi-automatic production lines, CNC-based material processing, and small batch flexibility to match diverse operator requirements. Dunlop maintains more than 500 approvals covering approximately 300 aircraft types. Retreading is a core technical competency. Tires selected for retread undergo stringent, non-destructive inspection, including full bead-to-bead chirography, leak testing, and detailed casing evaluation. Buffing, repair, skeeving, and bonding procedures follow strict dimensional and adhesion standards to restore casing integrity while maximizing lifecycle value. Retread plants in the UK, China, and North America reduce logistics time and support regional fleets. Dunlop's engineering team collaborates with universities and OEM partners on next-generation tire modeling, lightweight structures, advanced compounding, and foreign object damage-resistant architectures. Research includes intelligent tire systems with embedded health monitoring and RFID-based lifecycle tracking. Through vertically integrated manufacturing, rigorous quality management, and specialized retreading capabilities, Dunlop Aircraft Tires delivers aviation-grade tire systems designed for maximum reliability, performance, and safety.
At the Reifenmuller retreading facility in Hamelberg-Westheim, tire renewal is performed through a highly structured industrial workflow designed to restore performance, safety, and durability. The process begins in the carcass storage area and the loading and unloading hall, where used tires are received and prepared for inspection. Each carcass is subjected to a 100% incoming inspection using shearography, a non-destructive testing technology that identifies internal separations, air pockets, and structural damage with high precision. Approved carcasses proceed to computer-controlled buffing stations. Here, the worn tread is removed, and the surface is roughened to an exact profile, ensuring optimal adhesion for the new tread. Any defects detected during inspection are corrected in the repair stage, where damaged areas are carefully prepared and rebuilt to meet structural requirements. Next, the retreading phase begins. Binding rubber is extruded evenly onto the carcass, forming the adhesive layer. Using laser-guided ring tread laying technology, the new tread ring is applied with precise centering and uniform distribution around the tire circumference. This ensures balanced rolling behavior and consistent wear characteristics. Depending on the application, flat tread strips may also be applied, with additional binding rubber extruded to secure the tread system. The assembled tire blanks are then enclosed and transferred to the vulcanization stage. Vulcanization takes place in an autoclave at approximately 110 degrees Celsius, where controlled heat and pressure permanently bond the new tread to the carcass. For hot retreading, uncured tread rubber is applied and fully cured during this process. In the final stage, every tire undergoes comprehensive quality control, including visual inspection and automated pressure testing. Only tires that meet all technical and safety standards are released, ensuring reliable performance and extended service life.
In modern fleet operations, every kilometer counts, not only for performance but for profitability and sustainability. The Bridgestone Max-T Solutions compressed retread process is a precision-engineered system designed to extend tire life while meeting the highest standards of safety and performance. Operated under Bridgestone South Africa, the process combines access to premium tire brands with advanced retreading technology, producing retreads that comply with strict SAB specifications and match the safety standards of new tires. This solution not only reduces operating costs, but also supports sustainability, using less than 1/3 of the oil required to produce a new tire. Retreading begins with the collection and delivery of worn tires to the factory. Each casing is subjected to an initial visual inspection to identify any operational or non-operational damage from prior use. Only casings meeting exact SABS criteria are approved for processing. The first production stage is buffing, where the original tread rubber is removed in accordance with the manufacturer's specified buffing radius. Measurements of tread width and circumference determine the appropriate replacement tread size. Rubber shavings produced during buffing are collected and recycled. An air-pressurized grinding tool is used to remove dirt and rust from the belt edges, ensuring a clean bonding surface. Damaged crown areas are repaired through reinforced or sectional repair methods, restoring full structural integrity. The prepared surface is thoroughly cleaned, then coated with cement to prevent oxidation and ensure strong adhesion. Once dry, cushion gum is applied to fill skeeved sections in both crown and sidewall areas, preparing the casing for the new tread. The selected tread is cut to a length approximately 6% greater than the casing circumference. Both tread ends are cemented and left to dry, while a bonding layer is applied to the underside. The casing is inflated to 250 kilopascals to restore its shape, and a secondary inspection is performed to detect and repair any air leaks. The tread is positioned in the tread holder band and precisely aligned with the casing. Inflation to 700 kilopascals, combined with a 250 kilopascals bladder pressure, compresses the tread onto the casing for 60 seconds. This compression results in a denser rubber structure with enhanced cut resistance, puncture resistance, and mileage. Accurate tread application improves tire balance and minimizes the risk of splice separation during operation. Following compression, Sabes and Max-T identification labels are applied for tracking and quality control. The tire is placed inside a curing envelope to maintain an airtight seal. The assembly is mounted in the curing room, where an internal bladder inflates to secure the casing. The tire is then loaded into a 40-ton curing chamber or autoclave, where it undergoes curing at 500 kilopascals chamber air pressure and 700 kilopascals bladder pressure, with a maintained differential pressure of 200 kilopascals. Curing temperature is controlled between 115 degrees Celsius and 118 degrees Celsius for a period of 3 hours and 40 minutes. Each curing cycle is logged for traceability and quality assurance. Once cured, the tire undergoes cosmetic finishing and paint application. A final inspection verifies that all technical and safety standards have been met before the retread is cleared for delivery. This controlled, step-by-step process ensures a cost-effective, high-performance, and environmentally responsible solution for extending tire service life, reducing fleet costs, and lowering environmental impact. This is core. The Bandag retread process begins with a controlled workflow designed to restore commercial tire casings to safe, high-performance service. As each tire enters the plant, it is logged in the receiving area, where a work order is generated and a barcode is attached. This ensures full traceability throughout the production line. After receiving, the casing proceeds to the initial inspection, one of the most critical stages in the entire process. More than half of retread failures originate from inadequate inspection, so every tire undergoes a rigorous 7-step evaluation. The inspector mounts the casing on a mechanical spreader, allowing clear visibility of the inner liner, sidewalls, and bead regions. Both hands and eyes are used to detect embedded objects, cuts, and punctures. Any defects, such as nail holes, are marked for later repair. Following visual inspection, the casing is subjected to electrical inspection. Electric impulses help identify invisible punctures or separations beneath the surface. Any damage that cannot be repaired safely results in immediate rejection. The casing then advances to shearography, where advanced laser and vacuum technology create optical images of the tire's internal structure. This bead-to-bead scan reveals separations and structural defects that are not detectable by conventional inspection methods. Once approved, the tire moves to the buffer station. Buffing removes the worn tread and prepares the surface for bonding. The casing is inflated to standard running pressure, then buffed to a precise crown width, radius, and profile, ensuring a uniform surface for the Bandag procured material. Next is skiving, where damaged or rusted steel cords are removed and penetrations are cleaned out to solid material. Wire brushing and application of CIT compound prevent oxidation and create a tacky surface for proper adhesion. The repair stage follows. Technicians address more serious injuries, such as shoulder separations, crown damage, or bead area defects. Damaged material is removed, the injury is drilled from both sides, and the liner is buffed to the correct texture. Uncured rubber is extruded into the cavity, and a repair unit is stitched firmly into place. In the cushion application stage, a thin layer of uncured cushion gum covers the buffed casing, filling skive areas and forming the bonding layer for the new tread. During the building stage, a procured tread is measured and applied around the casing, its ends spliced, stapled, and stitched tightly to eliminate trapped air. The enveloping step seals the assembly in a flexible rubber envelope with arc rings at the beads. Vacuum testing confirms airtight integrity before curing. Curing is performed at tightly controlled temperature and pressure, bonding the tread permanently to the casing. Finally, the tire undergoes a detailed final inspection. Once verified, it is logged in Bandag's system and finished with weather-resistant paint, ready for return to service. Juva has evolved into a highly specialized truck tire retreading manufacturer, leveraging more than 2 decades of operational knowledge and adopting advanced systems from Bandag of the Bridgestone Group and the Austrian engineering firm Karg. This technical ecosystem forms a modernized production line designed for dimensional accuracy, structural integrity, and consistent adhesion throughout the tire remanufacturing cycle. All equipment used in the factory is heavily automated to minimize human error, stabilize process parameters, and eliminate defects that could lead to service failures. The retreading workflow begins with comprehensive carcass inspection, which is the most decisive stage for determining retread feasibility. Visual examination covers the inner liner, sidewall surfaces, bead zones, and external tread interface. The carcass is mounted on a rotating stand where foreign bodies such as stones, nails, and metallic debris are mechanically extracted. Damaged areas are marked and categorized based on repairability. Carcasses that exhibit structural compromises, bead separation, or critical ply damage are immediately rejected. To eliminate subjectivity, Juva employs Bandag's computer-controlled laser shearography system. A 1-atmosphere vacuum is created inside the inspection chamber, and laser beams scan the casing to reveal invisible internal separations, trapped air pockets, and voids between plies. This non-destructive testing method ensures that only structurally sound casings progress further. Carcasses that pass shearography receive 2-year guarantees due to the increased confidence in their structural health. The next major phase is buffing and surface preparation. The worn tread is removed on a CNC-controlled buffing station, where the tire is inflated, rotated, and machined by a high-torque cutter. The system shapes the casing to precise width, radius, and texture parameters required for optimal bonding. Digital profiles are preloaded into the management system to match tire dimensions and tread design. Any previously hidden defects often appear at this stage. Repairable zones are marked, while irreparable casings are diverted to recycling. In the repair stage, technicians restore cuts, punctures, and ply penetrations using specialized tools. Internal and external surfaces are ground, cleaned, and patched according to standardized repair protocols. Prepared cavities are filled with uncured rubber compounds to restore continuity and mechanical strength. Once repair is complete, the casing enters pre-vulcanization preparation. A liquid rubber bonding agent is applied uniformly across the buffed surface to create a chemically active interface. A new cushion gum layer is extruded onto the casing using a heated hand extruder to ensure uniform thickness and complete void filling. This intermediate layer is critical for anchoring the new tread during vulcanization. The tread application workflow begins with precise cutting and edge preparation of the unvulcanized tread belt. Joint edges are processed to ensure seamless pattern continuity. The casing is placed in a specialized inflation stand, brought to controlled pressure, and wrapped with the new tread. An enveloping system, consisting of a flexible outer sheath, inner tubes, and sealing rings, creates a vacuum that uniformly compresses the tread against the casing. The assembled tire is transferred by conveyor to the curing area. Cold vulcanization is conducted inside an autoclave at approximately 100 degrees Celsius under at least 6 atmospheres of chamber pressure. The compressed envelope ensures intimate contact between casing, cushion gum, and tread throughout the curing phase. This temperature range is intentionally low to protect the structural properties of the carcass plies while enabling full chemical cross-linking of the new rubber. Tires can undergo multiple retreading cycles using this method without compromising casing durability. After curing, final quality control is performed while the tire is still hot, allowing immediate detection of surface anomalies, bonding defects, or profile irregularities. Each tire receives a finishing coat of liquid gum to seal microporosities and achieve a uniform new tire appearance. Juva's strict adherence to industrial standards and its integration of automated diagnostic and curing technologies allow retreaded truck tires to meet the same functional requirements as new tires. With adoption rates exceeding 50% in major transport markets, retreading provides operators with a cost-efficient, structurally reliable, and environmentally sustainable tire solution. The proceso de envoltura in tire renovation is a controlled retreading method in which a worn tire is inserted into a new outer casing to restore structural integrity and extend service life. The operation begins by selecting and preparing the old tire, ensuring that its internal carcass remains sound and free from critical defects. After inspection, the worn tire is carefully inserted into a compatible outer shell, a reinforced casing that provides new tread quality and sidewall support. Once the old tire is positioned inside the new casing, the technician proceeds to insert an inner tube between the two layers. The tube is aligned circumferentially to avoid folds or pinches that could lead to uneven expansion or premature failure. With everything correctly positioned, controlled inflation begins, gradually expanding the inner tube so that the old tire and new casing bond tightly together. During inflation, a second tire is placed on top of the assembly to apply vertical pressure and maintain concentricity. This external load ensures that the expansion force is distributed uniformly, preventing distortion and ensuring the casing wraps evenly around the old tire. The technician monitors pressure, alignment, and bead seating throughout the process to guarantee consistent geometry. The result is a securely wrapped, pressure-stabilized, renovated tire, ready for further curing or finishing steps depending on the specific retreading workflow. Juba has developed a highly technical and automated process for truck tire retreading, ensuring that all retreaded tires meet the same standards as new products. The process begins with a comprehensive visual inspection of each tire carcass. Technicians examine the inner liner, sidewalls, bead edges, and tread surface to identify critical defects, including cuts, punctures, or embedded foreign objects. Stones, nails, and metal fragments are removed using precision tools to prevent damage in subsequent stages. Only carcasses passing this initial inspection proceed for further evaluation. The next stage involves advanced non-destructive diagnostics using Bandag's computer-controlled chirograph laser system. Under a vacuum of 1 atmosphere, the tire carcass is scanned with laser beams to detect hidden stratifications, voids, and internal defects that cannot be seen visually. Tires failing to meet the structural standards are discarded, ensuring only reliable casings continue. Once approved, the tire enters the tread removal stage. Mounted on a specialized stand and inflated, the tire is rotated while a precision cutter systematically strips the worn tread. This process shapes a perfectly round surface with controlled roughness to optimize adhesion for the new tread. Hidden defects identified during this stage are either repaired using specialized compounds or, if irreparable, removed from the workflow. The preparation for vulcanization follows. The tread area of the casing is coated with a liquid rubber primer, and grooves are filled with unvulcanized rubber. A new tread belt, cut to exact specifications, is applied and pressed against the tire casing in a precision inflation stand. This ensures the tread conforms accurately to the casing surface, guaranteeing uniform adhesion. Vulcanization takes place in a controlled autoclave chamber. The process maintains a pressure of at least 6 atmospheres and a temperature around 100 degrees Celsius. Cold vulcanization allows the tread to bond chemically with the casing without affecting the structural integrity of the carcass or cord layers. This method enables multiple retread cycles on the same tire while maintaining performance and safety. Throughout all stages, strict quality control measures are applied. Visual and instrument-based inspections are performed after tread removal, post-repair, and post-vulcanization. Any latent defects are detected and corrected immediately. Final inspections are conducted while the tires are still hot, and a liquid rubber coating completes the retreading process. The combination of highly automated machinery, laser diagnostics, and precision cutting ensures consistency and minimizes human error. Juva's technology accurately determines tire suitability for retreading, monitors defect repair, and controls adhesion and vulcanization parameters. Tires processed using the chirograph system carry a 2-year technical guarantee, reflecting the reliability of the workflow. Juva's retreaded tires meet all modern performance standards, offering durable, safe, and cost-effective solutions for transport operators. The integration of advanced equipment, technical precision, and comprehensive quality control underscores Juva's leadership in truck tire retreading and ensures that retreaded tires are fully reliable, safe, and efficient for heavy-duty applications. After the tires are fully loaded into the baler chamber, the second stage begins with the compression process. A high-capacity hydraulic cylinder exerts a controlled downward force onto the stacked tires. This compression eliminates trapped air, collapses the tire volume, and tightly compacts multiple layers of rubber, steel belts, and fabric plies within each tire. Heavy-duty farm and truck tires require exceptionally high hydraulic pressures, often exceeding 200 bars, to overcome the elastic resistance of steel-reinforced sidewalls and maintain uniform compression across the bale. Precision sensors continuously monitor both cylinder pressure and travel distance, ensuring that the tires achieve the specified compacted density without structural damage. Anti-kickback mechanisms and automatic pressure relief valves maintain operator safety throughout the compression cycle. Once the tires reach maximum compression, the baler transitions to the securing phase. Steel wire or strapping material is automatically fed around the compressed block. The tensioning system, either mechanical rollers or auxiliary hydraulic tensioners, applies uniform force, locking the compacted tires into a stable bale. Correct timing is critical. Straps applied too early may result in expansion after cylinder release, while delayed strapping can compromise bale integrity. Retention pins and clamps ensure the straps remain fixed as the hydraulic cylinder gradually retracts. Following securement, the chamber doors open, typically both front and rear, to allow controlled ejection of the finished bale. A secondary hydraulic ram or mechanical ejector system pushes the bale out onto conveyors or rollers, ready for storage, transport, or stacking. This automated ejection ensures minimal handling, reducing operator strain and the risk of deformation during removal. The complete compression, strapping, and ejection cycle is carefully timed. Small passenger or farm tires can be processed within minutes, whereas larger agricultural or heavy truck tires may require additional time due to their greater volume and structural stiffness. Throughout the process, real-time monitoring of hydraulic pressure, strap tension, and chamber alignment ensures consistent bale quality, repeatability, and safety compliance. This second stage transforms loosely stacked tires into dense, transportable bales that optimize storage space, facilitate logistics, and prepare the material for recycling or resale. By integrating automated compression, precision strapping, and controlled ejection, the system achieves high throughput while maintaining uniform bale size, structural integrity, and operational safety standards, making it a critical phase in the overall tire baling workflow. A semi-automatic tire building machine orchestrates the precise assembly of tire components into a uniform green tire, integrating mechanical accuracy with operator-directed control. The process begins at the building drum, where the bead setters, belt/ply guides, servo motors, and tension control systems are synchronized to ensure stable geometry throughout the build cycle. Operators load the inner liner and body ply rolls, and the machine advances each layer under regulated tension to avoid wrinkles, air entrapment, or variation in gauge. Once the inner liner is wrapped around the drum, the machine positions the first and second body plies using edge-guided rollers and vacuum-assisted alignment heads. Bead rings are then placed by semi-automatic bead applicators, which clamp and lock the beads to maintain diameter accuracy. The carcass is shaped using controlled inflation and servo-driven forming arms, transitioning the flat band into a toroidal profile without disturbing ply alignment. In the second stage building zone, steel belts and the tread package are applied. Precision servos position the belts at strict angles, while automatic splicing units trim and overlap the ends to ensure consistent stiffness and uniformity. The tread is then laid over the belt package with pressure rings that conform the entire assembly to final dimensions. Throughout the process, sensors monitor tension, splice accuracy, drum speed, and component offset. The semi-automatic configuration allows operators to intervene at key checkpoints while maintaining repeatability, making the system suitable for high-mix, mid-volume tire production, where dimensional stability and structural consistency are critical.